Alright, so we're going to finish up our discussion on radical reactions and finish up chapter 25. And so far in chapter 25, we talked about the radical reaction of alkanes. Now we're going to move on to talk about the radical reaction of alkenes and alkynes. So we're going to talk about the radical addition of HBr to an alkene, and it's going to give us the anti-Markovnikov addition. So I'm going to go back and revisit a reaction that we talked about in the spring. So we take an alkene, an unsymmetrical one, and we treat it with HBr. We get addition of the bromine to the more substituted carbon, so we end up with a product that looks like this. And we call that the Markovnikov addition. Product. And that's because we have the bromine add to the more substituted carbon. So remember, if we go through the mechanism for this reaction, our alkene is nucleophilic. We have a partially positive charge on the hydrogen, and so it swings out and grabs the hydrogen. We can either swing out and put the hydrogen on this carbon, or we can swing out this way and put the hydrogen on this carbon. So I'm going to draw out both of those. And if we put the hydrogen on this carbon, we now have a carbocation here. And if we put the hydrogen here, we have a carbocation here. This is primary, this is secondary, and so the secondary one is more stable, and so we do not generate the primary carbocation. The bromine, the Br minus that we generate in this step comes in as a nucleophile, and that gets us to our Markovnikov product. So now if instead we go through a radical reaction, we're going to get the anti-Markovnikov addition. So if instead of just using HBr, we throw in some peroxides, so something like hydrogen peroxide, we get the anti-Markovnikov addition of bromine. And so notice that our bromine adds to the less substituted carbon, and we call this the anti-Markovnikov addition product. And so let's run through the mechanism for this reaction. So I'll just erase that part there, and so I'll draw out my peroxides. Remember that a peroxide is an oxygen-oxygen single bond, and the R group can be hydrogens or carbon groups. And so we get homolysis of the peroxide because it is a good radical generator. And so we get our peroxide radical. This now goes on to react with the HBr. And so now this gives us our bromine radical. Once we've generated our bromine radical, it's now ready to react with the alkene. So we bring in the alkene. And remember that radical stability is exactly like carbocation stability. And so we want to generate, so we could either have the alkene swing out and attach to the bromine on this carbon, putting a radical here. So I'll draw that out. And that would be the result of the arrows that I've drawn here. Now if the bromine attached to this carbon and our radical ended up here, we would now have this. This is a primary radical, this is a secondary radical, this is more stable, and so this is what is formed. And so notice in the previous mechanism that I just talked about from the spring, we add the hydrogen first and then the bromine. And the radical reaction, we add the bromine first, and then we're going to add the hydrogen second. And so we bring back in another HBr molecule, and we pick up a hydrogen from that to give us our final product. And so this gets us to our anti-Markovnikov product. And it's these two steps here that we call the propagation step, which I talked about earlier in the this chapter. And remember, the propagation steps make up the overall reaction. And so if you mark out things that are on the product side with the reactant side, we get the overall reaction of taking the alkene with HBr and peroxides, and we get our anti-Markovnikov addition. And so bottom line is, if we use just HBr, we get bromine added to the more substituted carbon. If we use HBr and peroxides, we get addition of bromine to the less substituted carbon. Alright, so just like carbocations, radical intermediates are flat as well, or sp2 hybridized. And so our stereochemical outcome of a radical reaction is that we're going to get our two enantiomers. So we're going to have half of our product with the bromine, for example, pointing towards us, and the other half pointing away. So we take an alkane like we saw earlier in the chapter, and we treat it with bromine and some light. Then we're going to get addition of the bromine to the more substituted carbon because we generate the radical there. And we're going to end up with these two compounds. Remember, if we change all stereocenters that are present, these are enantiomers to each other. And if we make a 50-50 mixture of enantiomers, we call that a racemic mixture. And so we get a racemic mixture in this case. Now let's take a look at another example of our stereochemical outcome, especially if we already have a stereocenter. So let's draw up this molecule. Alright, so we take this molecule here, we have this stereocenter, and we throw in NBS and heat. Remember that if we use HBr, we're going to get a reaction with the alkene. But since we're using NBS, we're going to get addition at the benzylic carbon. So remember, the benzylic carbon is fairly stable, and so we can generate a radical there and get addition of our bromine at that position. And so again, once we generate the radical here, we lose our stereochemical information. It becomes flat, and our bromine can add to the back face or the front face, again giving us two enantiomers and a racemic mixture. And so let's take a look at one more example. So if we take this alkene shown here, and we throw in HBr and peroxides, then we're going to get addition of the bromine to the less substituted carbon, which we just talked about. The less substituted carbon is going to be this carbon here, and so we're going to have our bromine add to that carbon. This carbon does have 4 different things attached, and so it is a stereocenter, so we'll get a mixture of the bromine coming towards us. And the bromine going away from us. So once again, we get a racemic mixture of our two enantiomers. Alright, so we're going to move on to talking about dissolving metal reductions. And so remember, if you look at the periodic table, the sodium atom or the lithium atoms have a single electron for the sodium atom in the 3s shell, and for the lithium atom in the 2s shell. And so I represented that here by a single dot. And these atoms want to lose that electron in order to have a full octet. And so that's why we usually see sodium as Na+, because it gives that electron away. So we can do what's called a dissolving metal reduction, and we take sodium metal or lithium metal, put it in liquid ammonia, so that's what this L is here for, and that ammonia takes that electron away, and so we end up with Na plus and an electron. And so this electron doesn't belong to the sodium atom anymore, and it doesn't belong to the ammonia either. And so essentially we have an electron floating around that does not belong to any particular atom. And so that's why we call this a dissolving metal reduction. We end up with a single electron. Single electrons we represent as a single dot, and so it can act like a radical. All right, so we're first going to look at alkynes, and if we treat them with a dissolving metal reduction, so we take sodium metal, liquid ammonia, and we have to do this at really cold temperatures, so we do it at -78. We're going to get a dissolving metal reduction of our alkyne. So what happens is we add that electron to the alkyne and we end up with a transalkene. So I'll go through the mechanism in just a second. We have 1, 2, 3, 4 carbons here, so we have 4 carbons, and we get our transalkene. Remember, trans is when two groups are pointing in opposite directions. And so a reaction we learned earlier in the semester was we were able to make cis alkenes from alkynes. So let's revisit that real quick before I go into the mechanism. So we take the same alkyne and we treat it with hydrogen gas and Lindlar's catalyst. Remember that we get these cis alkenes. So we know how to take alkynes now and make them into transalkenes, make them into cis alkenes, and we also know how to take them all the way to the alkane if we treat it with hydrogen gas and palladium on carbon. All right, so let's take a look at the mechanism. So let's take our alkyne. Remember, if we have sodium and liquid ammonia, it generates an electron. So I'll draw a dot as my electron here, and it's going to combine with one of the pi bonds of the alkyne. And so once it does this, we now have 2 electrons sitting on this carbon and a single electron sitting on this carbon. If we have a lone pair of electrons, we put a negative charge. And so now this can act as a nucleophile, and it wants to do something as soon as it possibly can because a carbon with a negative charge is not very happy. So it pulls a hydrogen atom off of one of our ammonia molecules that's floating around. Remember, this is a solvent, and so it is very abundant in our reaction. And so now we have a species that looks like this. Once this occurs, our radical here combines with another electron that's been formed from our dissolving metal reduction. And now that gives us a lone pair on this carbon, making a negative charge. And the exact same thing happens again. Since this carbon's not very happy, it grabs a hydrogen from our ammonia molecule. And we get to our product here. All right, so as we've already mentioned, we're able to make transalkenes from alkynes. And so once we make the alkene, it still has a pi bond, but it doesn't react. And that's because alkenes are very sluggish in the dissolving metal reduction. And so once an alkene is formed from an alkyne, or if there's another alkene in the molecule, it doesn't react. And so we can selectively reduce alkynes over alkenes. We have an alkene here, we have an alkyne, we have a dissolving metal reduction, and so we're going to make a transalkene from our alkyne. So in total, we have 1, 2, 3, 4, 5, 6, 7 carbons here. That alkene over there is unaffected. And then we get a transalkene between these two carbons here. So if we count from this side of the chain, it's going to be 1, 2, 3. So that transalkene is going to be between the 2 and 3 carbons. So 1, 2, 3. So our transalkene is going to be here. And this will be the product of this reaction. All right, so one reaction I'm going to mention very briefly, but it doesn't have a whole lot of synthetic utility, is the Birch reduction. And so we can take a benzene ring, so an aromatic compound, we can do a dissolving metal reduction and get the reduction of one of these pi bonds. So if we take lithium metal, for example, and liquid ammonia, and we also have to throw in tert-butanol. So we have our dissolving metal reduction, we throw in some tert-butanol, we get out the non-aromatic product. And so notice that here we have 2 carbons that are sp3 hybridized, and they do not have pi bonds. And so this is non-aromatic, and this is what we call a Birch reduction. Again, not that useful in synthesis, and so that's all I'm going to say about this. All right, so to finish up the chapter, we're going to look at radical reactions in synthesis and essentially summarize everything we saw in this chapter. So one thing that's useful that we learned in this chapter is we can take compounds that have alkenes and we can treat them with NBS and light or heat. And we can get radical bromination at the allylic position. So remember, if we use NBS, it does not react with the alkene, but it can go to the allylic position, the benzylic position, or something like that. And so this is useful in synthesis. Another reaction that we've learned is the anti-Markovnikov addition of HBr. And so we throw in HBr, some peroxides, we get bromine added to the less substituted carbon. And so we call this the anti-Markovnikov addition. And so we can use HBr by itself to get bromine on the more substituted carbon, HBr and peroxides to get it on the less substituted carbon. Lastly, the other thing that we've learned is we can take alkynes and do a dissolving metal reduction in order to get the transalkene. And so out of this chapter, these are the most useful reactions. Take NBS in light or heat and allow us to put a bromine at the allylic or benzylic position. Take HBr and peroxides, allows us to put bromine on the less substituted carbon of the alkene. And dissolving metal reduction of alkynes gives us the transalkene. And so this reaction is complementary to the hydrogen gas and Lindlar's catalyst that we learned earlier in the semester, giving us the cis alkene.